So linear programming is what's going to help put a bow around the whole chapter, all the things that we've been talking about. So first of all, we've got a problem in which we have Monarch Leather Company, and it wants to add some handmade belts and wallets to its product line. So it has other products that it's producing, but it wants to see if it's going to be profitable and helpful to add some handmade belts and leather wallets to its production. And so each belt nets the company $18 in profit because it's handmade, it's something special, right? And each wallet nets the company $12 in profit. So we want, first of all, both the belts and the wallets have to be cut and they have to be sewn. The belts require 2 hours of cutting time and 6 hours of sewing time. Wallets need 3 hours of cutting and 3 hours of sewing time each. Mm-hmm. And they're leather, right? So you have to sew through leather. It's a whole different process. All right, so if the cutting machine is available 12 hours a week for this product, and the sewing machine is available 18 hours a week, we want to know how many belts and how many wallets should we make in order to make the most profit within these constraints. Meaning we don't get another sewing machine, we don't get more time on the cutting machine, right? We're stuck with these constraints, okay? So our whole goal here is to figure out what's the maximum profit. What's the maximum profit? So our objective, our goal, the whole reason we're doing this is to maximize our profit, right? All right, so how do we maximize that profit? Well, how many dollars do we make per belt? And how many dollars do we make per wallet? 18 and 12. So $18, is everybody okay if we let X be the number of wallets? Sorry, of belts? Might as well do it in order that it's written, right? And Y be the number of wallets? So that's our objective function, okay? We want to maximize that profit. A lot of times we let that just be Z. We say Z equals this. Okay? So far, so good? All right. Now we've got a whole lot of other stuff going on here. So we know that we are trying to make belts and wallets, and our belts were the X's. The wallets were the Y's. And we have to do two things to it. We have to cut and we have to sew, right? So every time that you see something like this, it's really helpful if you make a little table. Okay? How much time does it take to cut a belt? 2 hours. How much time does it take to sew a belt? 6 hours. Okay? How much time does it take to cut a wallet? And how much time does it take to sew a wallet? Okay, now let's think about cutting time. How many hours max do we have for the cutting machine each week? 12. Cutting machine's available 12 hours. Okay, so can it be less than or greater than 12? Less than. We don't get any more time, right? That's the most we get. Okay, so less than or equal to 12. We can have exactly 12 hours, right? But nothing more. And what about sewing time? 18. The max we get to use that sewing machine is 18 hours. And suddenly, if you make your table, the equations write themselves, don't they? Okay? What's our cutting constraint? Excellent. And what is our sewing restraint? All right. Can we make negative belts? No. So what does that mean? X has to be bigger than, could it be equal to? 0? Yeah. Okay, has to be positive, right? What about, can we make negative wallets? Mm-mm. So, okay, y has to be positive. So we're going to kind of lead you that way and always give you the first quadrant of a graph, right? But those are two valid constraints, and we need to make sure we write those each time. Okay, they're going to help us find our polygon that we will find the vertices of. All right, so far so good? Where was anybody lost? Anything that didn't make sense? Okay, good, good, good. All right, so next, what do you think we're going to do with what we've got here? Plot it. Go ahead and plot things, okay? So, do you want to use slope-intercept method, or do you just want to find the intercepts? You want to do slope-intercept? Okay. You can do that. The problem with doing slope-intercept form, though, is how do we figure out our scale? You have to rearrange it, and you can find out what your b's are, right? And then do we know what our values for x could be? Okay. So do you see why intercepts can be kind of helpful, because they can help you figure out how big x needs to be and how big y needs to be? Okay. So what if I cover up x and I say, okay, if x is gone in this first equation, what's y? 4. If y is gone, covering it up, what's x? 6. Okay, that's going to be my blue line. Second equation, if x is gone, x is 0, what's y? And then if y is 0, what does x have to be? So now we can see that the smallest value, or the biggest value x gets to be is 6, and my smallest value, or biggest value y gets to be is 6, right? So that helps me figure out what my scale is going to be. And these are 10 by 10, so is everybody okay with just leaving it as 1 for each one? Okay. So this one works out well. Okay. So plot your two lines. Going to be solid lines. And if I want it to be less than or equal to 12, which way am I shading? Towards the origin or away? Towards, right? Because 0 plus 0 is 0 plus 0 less than 12. Yep, so I know I'm going to shade toward the origin here. Okay, plot your second line. And that second line, are we shading towards or away? Towards again. 0 plus 0 is definitely less than 18. So we know we're heading in this direction. All right, x greater than 0, y greater than 0 means I'm heading out, up, and to the right. It's that little quadrilateral, right? So little quadrilateral right here is what's going to satisfy all 4 equations. That's where all 4 would overlap. All right, so 3 of the vertices are very easy to pick up, right? What are 3 of those vertices going to be? 0, 4, 3, 0, 0, 0. We don't know for sure, right? It didn't really cross in a nice, neat spot, did it? It's a little bit more than 1 and a little bit more than 3, but we don't know how much. It's too hard to tell by graphing, unless we have a very accurate graphing mechanism like a graphing calculator. Or could we solve these two systems? Okay, so what would we do if we want to make one of our variables disappear? We can multiply one of them by -1 and the y's would go away, right? Or just subtract. Or we could multiply the top one by -3 and the x's would go away. Okay, so let's just subtract. Do you want to take the second equation minus the first, or the first minus the second? Okay, second minus first. Let's go bottom minus top. Okay, so if I take 6x equation minus the 2x equation, I will end up with 4x. 3y minus 3y is gone. 18 minus 12 is 6, right? Good question. So why is it equal to? We've been dealing with less thans, right? But are we looking for a region, or are we looking for an exact point? An exact point. So it's okay to switch it to an equal sign because we're trying to figure out exactly where these guys cross. Okay, so 1.5 or 3/2, right? Okay, now that we know x is 3/2, which equation you want to plug it into? Top one. So 2 times 3/2. See why it's beneficial sometimes to keep things in terms of fractions? All right, so 3 plus 3y is 12. So what's y? Okay, so our x is 3/2 and our y is 3. You were saying 1.3 repeating, right? So you're close. Okay. We feeling good about these? So 4x equals 6, we said let's let the x be, where did we do this? We said, yes, top minus bottom. Okay, so 6x minus, so this is where this came from. Okay, these things take up a lot of space, so we end up being a little bit all over the place. Okay, so we found vertices. Yay! Okay, almost. Okay, here's the last piece. What was our whole objective? Which of those 4 points is going to maximize our profit, right? Okay, so this is what we did yesterday, right? But today we add that one last step. We say, hey, now I've got these 4 vertices. I want to see when do I maximize my profit. Okay, what's the best scenario? All right, so plug them all in. If we plug in 0 for x and 4 for y, absolutely, that's the whole goal. No point to do in doing the origin, right? We're not going to get any profit, are we? Okay, so 18 times 0 plus 12 times 4 gets us yeah, I mean, we got to see which one's going to give us the best value. Question. We think it's probably the last one, right? And that's a question for the production manager, right? Is there a good time? Is it possible to make a half a belt, right, on one day and then finish that belt the next day without causing problems with the whole production line? Mm-hmm. Right. So it might take that time. The next day they may just pick up that belt and finish it the next day, so they know that every other day they're going to have a half belt left over, and the next day they start with that one. Yes, sir. It's always going to be, okay, good question. So is the maximum always going to be one of these vertices? Okay, and not necessarily. Okay, sometimes it will be one of these other ones, right? It will be worth it not to make belts. It's better to just make wallets or vice versa. Okay, so we want to try them all. Okay, now sometimes though there's a range of values that happens. It may be possible that we get the same profit when we plug this vertex in as when we plug this vertex in. Everything in between would be valid, and they just decide which ones they want to do. Okay, does that make sense? Yep. That's why we plug them in and see. All right. So 18.0 we found was a $48 profit. 30, or sorry, 0.4 gave us a $48 profit, and 30 is going to give us how much? $54 profit, right? And 00 is going to give us $0 profit, right? So it makes no sense not to do any of these belts and wallets. And then finally, let's try the 18 times the 3 halves plus 12 times 3. 63. So when did we get the most profit? 1.5 belts and 3 wallets, right? Okay, so we maximize the profit when 1.5 belts and 3 wallets are produced for $63 in profit. Make sense? Okay. These take time, don't they? A lot of time. Okay. All right. Shall we set the next one up? Okay. And I think those of you who are working book assignment, that's okay. You can do book assignment instead. But I'm going to let you guys finish the second one that we'll set up here in just a moment, and then do 3 and 4, and you'll be done. You don't have a book assignment then. Okay? So those of you who have already started on book assignment, you're fine. You'll get the same kind of practice, right? So you can do that instead, or you can decide to join us for number 2, go back and do number 1, and make sure 3 and 4 are done. Make sense? Okay, so 3 and 4 are homework, and the rest of 2. We're going to start setting it up, but I don't know that we'll have time to finish. Absolutely. You're welcome. Okay, here comes the next one. So we've got Toys by Grant making toys at 2 different plants. Okay, and we need to make, plant A has to make a minimum of 10,000 toy dump trucks. Sorry, 1,000, thank you. And fire engines total, right? So 1,000 toys altogether, okay? Otherwise, it's not efficient to have our plant going, and we have to lay people off and so forth, okay? Plant B has to make a minimum of 800 toys in order to be productive, and plant A can make 10 dump trucks and 5 fire trucks in an hour. B can produce 5 dump trucks and 15 fire trucks and fire engines in an hour. It costs $30 an hour to produce toy dump trucks and $35 per hour to produce toy fire engines. So we want to know how many hours should be spent on each toy in order to minimize the cost, and we want to know what's the minimum cost. All right, so what's our objective here? Minimize the cost, okay? So our objective, our goal is to minimize cost. Okay, so we have to minimize the cost, and where are our costs involved? Per hour, right? We have a rate, okay? $30 per hour to produce dump trucks and $35 per hour to produce fire engines, okay? So we're trying to minimize, our Z function is $30 per hour times however many hours we're producing dump trucks. Z is just a number, or just a letter. That's typically what we use for our objective function, its value. Okay, and then $35 per hour times however many hours we are producing fire engines. Okay, so X is not the number of fire trucks we're making, right? What is X? The time. X is the number of hours we're producing dump trucks, right? And Y is the number of hours in fire engine production. So let's make a table, okay? So we have problem, right? Because we can make 10 toy dump trucks. So we have two plants, right? Okay, plant 1, or plant A, and plant B. Okay, and plant A can do what? All right, so dump trucks, fire engines. X is the number of hours we're using dump trucks, or making dump trucks. Y is the number of hours we're making fire engines. So 10x, right? Okay, so 10 per hour times however many hours, right? Plus 5 fire engines times however many hours they're making fire engines, right? Is going to, now think about this, 10 dump trucks per hour times hours. Hours are going to cancel, aren't they? Okay, we have dump trucks per hour times hour. What's my net result? The trucks. How many trucks can we make at plant A? A minimum of 1,000, right? We're talking dump trucks times hours, fire engines times hours, right? So we're getting dump trucks and fire engines total of 1,000. So is this a less than or a greater than or equal to? Greater than. We want to have at least 1,000. Can be equal to as well. Okay? That's one of our constraints. 10x plus 5y greater than or equal to 1,000. All right, plant B. How many dump trucks can it produce in an hour? 5, right? Times however many it's produced, how many hours it's producing, right? Plus 10, 15 fire engines times however many hours it's producing fire engines, right? And that's got to be greater than or equal to so write that constraint. So far so good? Can we work for negative hours? No. So can't produce for negative hours. So we have to be in the first quadrant. Those are always going to be two of our objective functions or constraints. Because we could decide that we don't want to spend any hours working on dump trucks. It might be more efficient to just make fire engines, or vice versa. Okay? So it's possible that we'll produce 0 of one of them and the whole thing of the other. One might be so much less costly. Yes, sir. Once we find our vertices. Okay? So next step, graph these, right? Figure out where your vertices are, and then plot those vertices into your objective function to figure out which one minimizes the cost. Make sense? Okay. Last time we were looking for maximum profit, so we were looking for the biggest number. This time we're looking to minimize the cost, so we're wanting the smallest z value. Maybe not. I don't know. Maybe. The problem is, think about what's happening here, right? We're going to be having some kind of a line, right? And another kind of a line. But we said, wait a minute, we've got to be as big as possible this time, right? So are we shading in the direction of 0, 0? We're going to be shading outward, aren't we? So we'll have an unbounded graph, and we want to figure out which of those three vertices is going to give us the minimum cost in labor hours or production hours. Make sense? All right. I'll leave you to it.